Hello again. This is section 4.4, laws of logarithms. So what we're going to look at in this section is how can we use some properties of logs to actually combine logs or expand logs, and then eventually this is going to help us when we move into solving equations in our later sections in the unit. Okay, so our laws of logarithms here, first we're going to let a be a positive number, and that's little a, where a is not equal to 1. Then we're going to let a, b, and c, all capitals, be any real numbers with a greater than 0 and b greater than 0, meaning a and b both need to be positive. If that's the case, then the base a log of a times b can be rewritten as two separate logs using addition now. So we're going to have the base a log of a plus the base a log of b. Now, same thing if we have division inside, we have the base a log of a divided by b, we can split that into two separate logarithms. That's going to give us the base a log of a minus the base a log of b this time. So division becomes subtraction when we split them into two logs. And then our last one here, we have the base a log of a to the c power. That exponent now can be brought out front and multiplied, and so we end up with c times the base a log of a. So those are our three laws of logarithms that are going to help us either to work from the right-hand side to the left-hand side, or sometimes to expand from the left-hand side to the right-hand side. Because these are equivalent, so we can move in either direction. So our first example here, we want to evaluate each one of these expressions. Now to do that, we're actually going to condense these logs into a single log, and then we're going to figure out what they're equal to. First thing you always want to look for is to make sure that the base is the same for each of your logs. So for this first one here, we have two base 4 logs. We have addition, so that means I can combine these and I can use multiplication. So this is going to become the base 4 log of 2 times 32. Now at that point, we can go ahead and multiply what's inside. So we have the base 4 log of 64. And if you remember from the previous section, to evaluate that now, we're asking ourselves 4 to what power will give us 64? Well, in this case, 4 to the 3rd power is 64, so that answer is going to be 3. Now the next one here, first step again, always make sure your bases match up. These are both base 2 logs, so this works. We're going to combine these now into a base 2 log of, and because it's subtraction this time, it's going to become division. So 80 divided by 5. Now we divide. 80 divided by 5 is 16. So we have the base 2 log of 16. And now we ask ourselves 2 to what power will give us 16? That's going to be 4. And so the value of that logarithm is going to be 4 this time. Then this third one here, we're using that last law of logarithms. We have a value out front. That means we can move it into the exponent. So this is going to give us the log of 8 to the negative 1/3 power. Now we need to simplify 8 to the negative 1/3. So the first thing I'm going to do is move that to the denominator to make it a positive exponent. So we'll have the log of 1 over 8 to the 1/3. Now remember, 8 to the 1/3, we could rewrite that as a radical. That would become a cubed root. So now we have the log of 1 over the cube root of 8. Cube root of 8 is 2, so we have the log of 1 over 2, or the log of 1/2. Now remember, with a log like this, the base is understood to be a 10 because this is a common logarithm. There's nothing I can raise 10 to give me 1/2. So I'm going to have to just use my calculator here, get a decimal approximation for this one. We're just going to put log of 1/2 in there. And if we do that, that should give us approximately negative 0.301. Example 2. So now we want to use laws of logarithms to expand each one of these expressions. So the first one we were condensing first so that we could evaluate. Now we actually want to work the other direction and expand these out. So what I noticed with this first one is I actually have multiplication inside my logarithm. That means I can split this into two separate logarithms using addition. Keep the base the same. So this is going to be a base 2 log of 6 plus, and then we're going to have another base 2 log of x. And that's all we can do in terms of expanding, right? Because we've used all of our laws of logarithms that apply to this one now. And let's take a look at the next one. I have a base 5 log. This time I have multiplication inside, so I'm going to do the same thing, split it into 2 separate logs. So we'll have a base 5 log of x to the third plus a base 5 log of y to the sixth. Now this time, I still have something else I can do because there's another law of logarithms that I can apply. I have exponents in both of these logarithms. I can move those exponents to the front. So now I can rewrite this as 3 times the base 5 log of x plus 6 times the base 5 log of y. And at that point, there's nothing else inside the logs that can be simplified using our laws of logarithms, and so we're going to stop right there. And this last one here, we have division, we have multiplication, and we have a radical. So there's going to be several things that we can do. The first thing I'm going to do this time is go ahead and split up my multiplication and division using addition and subtraction. So this is going to become the natural log of A plus the natural log of B, that takes care of the multiplication, minus the natural log of the cubed root of C. Now, natural log of A and natural log of B, there's nothing else I can do to that. But remember that cube root of C we could rewrite as a fractional exponent. So I'm going to change this now to natural log of A plus natural log of B minus the natural log of C to the 1/3 power. And because I have an exponent now, I can actually move that exponent to the front of my logarithm. We'll end up with natural log of A plus natural log of B minus 1/3 natural log of C. And now when I look inside each of my logarithms, there's nothing else I can do because there's no multiplication, no division, no exponents. So that is completely expanded now. All right, so now we're going to rewrite each one of these as a single logarithm, again, using our laws of logarithms to do so. We can't actually evaluate these because they have variables in them, so we just want to rewrite this as a single log. So the first thing I'm going to do, we always want to take care of that third law of logarithms first. If we have it, we want to move anything we can to the exponent. So my first logarithm here, I have this 3 out front. I can move that into the exponent. So this is going to become the log of x to the 3rd power. Then we have our plus. Now this 1/2, I can move it into the exponent. Notice there's a grouping here with parentheses, so that 1/2 actually goes on the outside of those parentheses. So this is going to be the log of x plus 1 to the 1/2 power. At that point, we have addition. That's going to become multiplication because we have 2 common logs this time, so we can combine them. We have the common log of x cubed times x plus 1 to the 1/2 power. And don't try to simplify any of that. We can't distribute the x to the 3rd power because that x plus 1 is being raised to the 1/2. So that's as simplified as we can make that one now. All right, same thing with the next one. The first thing we want to do is take care of those exponents. We're going to move the 3 into the exponent first. That'll give us the natural log of s to the 3rd. Plus, we can move this 1/2 to the exponent. It's going to give us natural log of t to the 1/2. Then we have minus. This 4 right here can get moved into the exponent. Again, we have a grouping symbol, so the 4 goes on the outside of that. So natural log t squared plus 1 to the 4th power. Now we can take care of our multiplication and division. Okay, so we have the addition for the first 2. That means the s cubed and t to the 1/2 are going to get multiplied. And then we have the subtraction, meaning that everything in that log is going to get divided. Since they're all natural logs, I can put them all together. We're going to have s cubed times t to the 1/2 divided by t squared plus 1 raised to the 4th power. Again, once you get it into a single logarithm, there's nothing else we can do there because that's what we were asked to do, is write it as a single log. And so that is our final answer. Example 4. Okay, so if a task is learned at a performance level P sub 0, that's our initial learning, then after a time interval T, the performance level P satisfies this equation. We want to solve that equation for P. Okay, so that's going to be our first step, and then we'll answer the questions at the bottom based off of that. Well, in this case, the first thing I want to do is I want to try to combine what I can on the right-hand side of this equation, because we're eventually going to try to get P by itself. I'm going to rewrite this now as log of P equals, well, first thing I notice is I have a C in front of this second log, so I can move it into the exponent. So we're going to have a log P sub 0 minus log T plus 1 to the C power. Now that I've taken care of my exponents, now I have subtraction, so that's going to become division. So we'll have the log of P is equal to the log of P sub 0 divided by T plus 1 to the C power. Now, at that point, because we have a log of P and we have a log of this other stuff, we can actually just drop the logs from each side, because if we have a P inside one log and this P sub 0 over T plus 1 to the C power inside of another log on the other side, if those two things are equal, then the stuff inside the logs must also be equal. And so this tells us then that P is equal to P sub 0 over T plus 1 to the C power. Once we get it down to a log on one side and a log on the other side, the stuff inside each of those logs has to be equal to each other. So we've answered that first part, we've solved for P. Now it asks us, if your score on a history test is a 90, what score would you expect to get on a similar test after 2 months? Okay, and we're assuming here that our C value is 0.2. Well, what we're asking then is, if our initial score is a 90, that's our P sub 0. That's the first time we take the test. We're going to wait 2 months now. That's going to be our time. That's our T value. And then they give us the C value here is 0.2. So all we want to do is substitute 90 for P sub 0, 2 for T, 0.2 for C, and then we're going to solve for our P, and that would tell us what we would expect to get on that test after 2 months. We have P equals P sub 0, which is 90, divided by T plus 1, so that's 2 plus 1, raised to the C, which is 0.2. Now at that point, we can just go to our calculator, and we can do all of that. We have 90 divided by, if you want to do 3 to the 0.2, you could do that. And that tells us we get approximately 72.2, and so about a 72 if we're just rounding that to the nearest whole number. So in other words, if we made a 90 on a test and we went 2 months without actually studying anything, right, assuming that we're going to forget things along the way because we haven't used them, we would expect to get about a 72 on that same test after 2 months. Then we want to figure out after a year. So again, I'm looking for the P value. P sub 0 is still 90. That hasn't changed. This time, though, after a year, remember T we used 2 for months. That means after a year, our T value is going to be equal to 12, because that will be 12 months in 1 year. We're going to do 12 plus 1, and our C value is still 0.2. So again, we're just going to substitute in this case 12 plus 1 instead of the 2 plus 1. So that's 13. And if we do that, if we round this to the nearest whole number, we should get about 54. So again, assuming that you got a 90 on a test the first time you took it, if you waited a year, didn't really study, and you forgot some stuff, you could probably expect to get about a 54 the next time you took it after a year. Okay. All right, now change of base. This is useful, especially on calculators that don't allow you to automatically just change your base of a logarithm. Again, some calculators do now, but a lot of them still do not. And so this formula actually allows us to rewrite any log that we have using our change of base formula so that we can actually input it into the calculator. So if you have a base b log of x, we can rewrite that as a base a log of x divided by a base a log of b. Okay, so notice here the x goes to the numerator, the b goes to the denominator, and then we have to use the same base, whatever base you would like, for the base a. Again, the reason this is useful is because it allows us to put it in the calculator, so the most common logs we're going to use are the common log or the natural log. So I could really write this as like log of x over log of b, or natural log of x over natural log of b. And again, it doesn't matter what base you choose here, either the common base of 10 or the natural base of e. Those two fractions are going to give you exactly the same answer in this case, no matter what. So again, if you have a calculator where you can actually input a base of b, by all means, just use that. But if you don't, then we need a way to actually put some of these in the calculator, and this change of base is what's going to allow us to do that. All right, so we want to use our change of base formula, and then we're going to actually use our calculator to evaluate these. So first thing we want to do here, I'm going to rewrite this using my change of base. Remember, the 5 goes to the numerator, so we're going to get log of 5 over, and then the 8 goes to the denominator, so we get log of 8. And again, you can use whatever base log you want, but we want to choose one that we can actually put in our calculator, so that's why I went with common log. Now, if we input this into the calculator now, log of 5 divided by log of 8 should give us approximately 0.77398. Because it does ask us for 5 decimal places here, so 0.77398 would be our answer. Now remember, we could also use natural logs, right? Because natural logs work in our calculator. So the second one, I'm going to use natural logs instead. We do the natural log of 20 divided by the natural log of 9. Again, I can put that into the calculator, round that off to 5 decimal places. Okay, so if we were to do that, we get 1.36342. And again, if you had done common log of 20 over common log of 9, it would give you exactly the same answer, right? So it doesn't matter what base log you choose, as long as you use the same one in the numerator and denominator. In this case, the 20 has to go in the numerator, the 9 has to go in the denominator. All right, so now we want to use a graphing calculator to graph this function. We have a base 6 log of x. And again, some calculators will allow you to actually input a base 6 log of x, and if it does, great. But if you have a calculator that doesn't allow that, then we're going to actually have to use change of base to rewrite this first, then we can graph it. So I'm going to rewrite this now as f of x equals log of x divided by log of 6. And then once we have that, then we can actually graph it. I'm not going to actually do that on screen here, okay, but just remember, any logarithm in general is going to have a vertical asymptote along the y-axis. We're going to have a y-intercept of 1, and it's going to go up and to the right, something like this, okay? But again, that will allow you now to put these things into Desmos and graph them if you want to, okay, because now we can use change of base to actually type those in. All right, so that's all we have for our laws of logarithms. Again, as always, let me know if you have any questions. Send me questions through WebAssign as you have them. Come see me during student hours. Have a great day, and I will see you next time.